Okay, so this video is about the definition of derivative. First of all, this is the definition of derivative, and it might sound familiar. The derivative of a function, f, at any number, a, denoted by f prime of a, that apostrophe means prime, denoted by f prime of a, if f prime of a equals to the limit of h approaches 0 of f of a plus h, subtract f of a divided by h. If this limit exists. So if that limit exists, then the derivative is going to be this. You might remember this formula being, this whole entire formula, this limit as h approaches 0, being part called definition of slope. Well, derivative essentially means slope of the tangent line. That's why the definitions are exactly the same. They're the exact same thing. So we're going to talk about this function a little bit more in depth today, and we can get more practice with this understanding derivatives. All right, so if you need this definition, I'll copy it down before you leave the screen. I'm about to erase it though. All right, so my question is, so what does derivative mean anyway? Well, let's talk about it with bubbles. It means three things. It means slope of the tangent line. So slope of the tangent line. It also means instantaneous velocity. And it also means instantaneous rate of change. So these are the three things that the word derivative actually means in calculus and elsewhere. It means slope of the tangent line, instantaneous velocity, instantaneous rate of change. So whenever you hear derivative, whether you're in calculus or physics or whatever, or any other math class, or any class that deals with, anyway, that's how it's accepted and understood all over the world. All right, now this is first derivative. This is all the things talking about today deals with first derivative. At some point we'll talk about second derivative, and that means acceleration. But today's video is all about first derivative, and first derivative means these three things: slope of tangent line, instantaneous velocity, and instantaneous rate of change. And again, second derivative means acceleration, but that's a future lesson. Okay, moving on. Okay, so first of all, derivative is written as f prime of x. That means this actually reads f prime x. Or the derivative of f with respect to x. You could also see it, because f of x means y, you can also see it as y prime. That apostrophe means prime, which reads y prime. Or you could see it as dy dx, pronounced dy dx. Or the derivative of y with respect to x is what it means. You could also see it as df dx, pronounced df dx. Or the derivative of f with respect to x. You could see it as d dx f of x, pronounced d dx of f of x. Or the derivative of f with respect to x, or derivative of f of x. All right, something worthy of note is dx does not mean d times x. It's not what that means. Also, dy does not mean d times y. It's not what it means. Also, dy dx does not mean dy divided by dx. It looks like it, it's written that way, but it's not what it means. Except when it's convenient to think of it as division. Also, df dx does not mean df divided by dx. It means df dx. So it looks like division, but it isn't. All right. Also, d dx of f of x does not mean d dx times f of x. So it does not mean times, just because there's no sign between there. In other math classes, we understand that as multiplication, but it's not what it means here. Except when it's convenient to treat it that way. All right, moving on. All right, so in the future, all this will come clear. So let me explain now. Suppose I gave you this function f of x. All right, so the derivative is the slope of the original function. So if I gave you this function f of x, derivative is the slope at each point on this function. So if I look at this first interval, that's from 0 to 1. So from 0 to 1, the slope is, we got to figure out the slope there. So it rises 2, runs 1. Slope is rise over run. So since it rises 2, runs 1, the slope is 2, positive 2. Rises 2, runs 1. That's the first interval. The second interval I could consider was the interval from 1 to 4. So from 1 to 4, the slope is, take a look at it, it rises 1 and it runs 1, 2, 3. So it rises 1, runs 3. The slope is 1 over 3. And the next interval is from 4 to 6, because there it's still the same. So from 4 to 6, the slope is, if you notice, it doesn't rise or fall. It just runs. So that slope is 0. It's a flat line. The slope is 0 there. And our final intervals from 6 to 9, you can't see it, but it's there. So 6 to 9, that slope is, all right, so we got to look at what happens. It falls this time from 3 to 0. So it falls 3, so I'm saying -3. And it runs 6 and 9, that's 3 again. So it's -3 over 3, which is -1. So the slope on that interval from 6 to 9, the slope is -1. So again, this is how we write it for the slope for each one of those sections. This is very unique because slope is constant there, and some functions work that way. We got constant slopes. Usually we think about quadratics and cubics where they move smoothly, not necessarily in straight lines, but this one does. All right, so if we want to graph the derivative, we'll be graphing y prime or f prime of x. So in just a moment, we're going to graph that beneath. Somebody erase all these little slope statements. We're going to graph y prime, f prime of x, and explain what the graph should look like. All right, let's go. All right, so looking at this, this is y equals f prime beneath. So if we get the derivative of f prime, f is f prime, and we can graph each of those slopes. The first slope was from 0 to 1, and that slope was 2. So it's a horizontal line. It's a constant slope. Slope does not change from 0 to 1. It's constantly the same thing. 0 to it's constantly 2. Now we define it on the left and right ends. So we got a closed dot on the left side, and every other dot is going to be closed all the way to the very end. And the reason why is here is a corner, and derivatives are not defined at corners, as sharp edges like this, because it's slope. And technically, if I want to draw a line there, a tangent line to that point, I can draw it in a lot of different directions. So because of that, that tangent line could look all kinds of ways. It could look this way. All right, so the slope is a tangent line to that point. The tangent line there would merge into the line up to this corner here. And I could draw a tangent line there, but because it's a corner, I can draw an infinite amount of tangent lines, and they could all be tangent to that corner. So slopes aren't defined, derivatives aren't defined at corners or sharp edges like that, because you can get multiple ways of representing that corner with the slope. I mean, infinite ways. So because of that, we don't find it there. So at the end, we have an open circle. That's going to be true for every point in between. But it needs to be closed at the beginning and end. So we just give it a closed dot at the beginning of the derivative function, and we give the closed dot at the very end of the derivative function, just because it's closed on those intervals, but nowhere else. But anyway, so let's keep talking about the other slopes. All right, so from 1 to 4, we said that the slope was, we said that the slope was, just explain what I just said. It said the slope was 1/3, so it should be down there. And then from 4 to 6, we said the slope was 0. So if you can see that, a little flat line came there where y equals 0. And from 6 to 9, we said the slope was negative 1. So that should be on line with -1 from 0 to 9. And notice how they closed it at the very end, because it just closed at its ends. But at the points in between there, because you have these corners, we can't actually give derivative values there. All right, let's go for it. Okay, so this is a pretty easy one. All right, so suppose you wanted to find the derivative of y equals x squared and later write the equation for the tangent line at the point 3, 9. All right, so you want to find the derivative of y equals x squared. It goes back to that limit formula we started with. Let's start with that. So this is our limit. Basically, you want to take the function f of x squared, and replace a plus h and a into it. So it will become the limit as h approaches 0 of, since f of x is x squared, this is going to be a plus h squared, subtract a squared over h. Now technically we know a. A is the x value in question, and that's 3. So I can replace all the a's that were 3. So let's do that now. And now replace all the a's with 3. Now, these usually work out really, really nicely if you do it properly. If you do it correctly, like rationalize the denominator, sometimes you may have to rationalize the numerator, sometimes you may have to factor. If you do it properly, the h's eventually cancel out, and we can find the limit there without having something that's undefined. So I'm going to square this binomial. I'm going to square 3, and this is the new expression. So when you square 3 plus h squared, it becomes 9 plus 6h plus h squared. Subtract 3 squared is 9, and it's over h. So you should see some things cancel for you, like this 9 cancels with that 9. And it winds up being something really simple. I'm going to rewrite this and finish it because I'm out of space, so I might have to erase some of this other stuff. But I'm going to make room to rewrite this. Okay, so after we cancel out these 9s, we wind up now having the limit as x approach, well, not x, h. H approaches 0 of h squared plus 6h over h. And what makes it really easy is these two are common factors, h and h. So I can factor out an h. I can call it the limit as h approaches 0, h times h plus 6. And you notice the h's cancel. So this cancels with that one, and it becomes the limit as h approaches 0 of h plus 6. And if you want to find that limit, you can evaluate 0 in 0 plus 6. So that limit is 6. So I know that the slope of the tangent line there is 6. So write the slope of the tangent line is 6. Or you might say m equals 6. You might say m equals 6. However you want to think about it, that's the slope of the tangent line. If you remember, there was a second part to our statement. So I'm about to erase all of this. So you need that as a note. I'll pause the video and copy it. I'm about to erase it and talk about the original statement. Okay, so the original statement says, suppose we wanted to find the derivative of the function, and we wanted to find it at the point 3, 9. So we found the derivative of the function at the point 3, 9. And that's the slope of the function at the point 3, 9. And we said that slope is equal to 6 when x equals to 3, or when a equals to 3. So that's what the slope is there. So what we want to do now is write the second part says write the equation for the tangent line. So I'm going to actually do that. I need a formula for it, and this is the formula I would use for it. Y minus y1 equals to m times x minus x1. That formula has a name. It's called the point slope formula. The reason why is you needed 1 point and 1 slope. You can write the equation for that line equals y equals mx plus b form. We got a point, and we also have a slope, so we can use the point slope formula to write the equation for tangent line at that point. So let's do it. I'm going to erase the screen. Okay, so this is what we know. For the points 3, 9, and we know the slope at x equals 3 is 6. So this is really x1 and y1. So when I plug them all into the equation, I should have y subtract 9 equals to 6, so that's m, times x subtract x1 is 3. So this becomes y subtract 9 equals to 6x subtract 18. Our goal is to solve for y, so we add 9 to both sides. So you get y is equal to 6x subtract 9. And this is the equation for the tangent line. This is the equation for the tangent line at x equals 3. Y equals 6x subtract 9. All right, so that's all I have to say for now. Good luck.